Hi, everybody. It's Professor Mitchell, continuing with Chapter 7. Today we are talking about 7.2, estimating a population mean. So in this section, we're going to present methods for using a sample mean, x bar, to make an inference about the value of the corresponding population mean, mu. Remember in the last section, we did this for a sample proportion. We used a sample proportion to make an inference about the value of a population proportion. So we're going to be talking about point estimates, confidence intervals, and sample size, the same things we talked about in section 7.1. So the appearance is to construct a confidence interval used to estimate a population mean. Your textbook focuses most of their attention on the case where the population standard deviation is not known, because that's the most likely situation. Remember, I don't know the population mean, so it's not likely I would know the population standard deviation, but we will, at the end of this, touch just a little bit on how it's different if you do happen to know sigma. So the notation we're going to be using in this section is mu for the population mean, n for the sample size, x bar for the sample mean, e for the margin of error, and s for the sample standard deviation. So the requirements to do this, your sample has to be a simple random sample, and your population either has to be normally distributed or n has to be greater than 30. Remember, these are the same requirements for a sampling distribution to be normally distributed. All right, so here is the formula for the margin of error to estimate a population mean. The margin of error is equal to t sub alpha over 2, and we'll talk more about what that is in a little bit, times s, the sample standard deviation, divided by the square root of n. Okay. And when we talk about t, I will talk about what this means over here. df stands for degrees of freedom. That's something you need in order to get the value of t sub alpha over 2. So the confidence level is associated, the confidence interval is associated with a confidence level such as 0.95. Remember in the last section, we talked about the most common confidence levels are 0.90, 0.90, 0.95, and 0.99. It is possible to talk about other ones, but those are the most common ones. So for example, if your confidence level is 0.95, then alpha is 0.05. 0.95, you'll remember from the last section, represents area under the normal curve in the middle of the normal curve between your two critical values. So the 0.05 would represent the area outside those critical values. All right, so let's talk a little bit more about this t. T sub alpha over 2 is the critical t value separating an area of alpha over 2 in the right tail. So before I go on, let me just point out that this is the same way that z sub alpha over 2 was defined before, okay? Except when it was z sub alpha over 2, we were talking about the standard normal distribution. Now we're talking about something called the student t distribution. So another number that you need when you're dealing with the student t distribution is something called degrees of freedom. In this case, the degrees of freedom is just n minus 1. So n is the sample size. For example, if the sample size was 20, then you would be looking at a student t distribution with 19 degrees of freedom. Okay, a little bit about rounding rules. I believe these are the same rules that we used in the last section. If you're using an original set of data, you want to round your confidence interval limits to one more decimal place than is in the original set of data. However, if you're working from summary statistics, such as X bar. Excuse me for 1 second. I think I just spotted a typo here. This should be an X bar. Okay, there we go. All right. So if you're working from summary statistics, then round the confidence interval limits to the same number of decimal places that are used for the sample mean. Okay. So student t distribution. If a population has a normal distribution, then the distribution of this variable, t, which is x bar minus mu, divided by s. Okay. That is another random variable, and the distribution of that random variable is called a student t distribution for all samples of size n. A student t distribution is commonly referred to as just a t distribution. So that's probably how you'll hear me talk about it from now on. All right, so again, finding a critical value t sub alpha over 2 requires a value for the degrees of freedom. Just a very little bit about what that number means. The number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. So in this case, that number is n minus 1. You're free to choose n minus 1 of your sample values, but once you've chosen all but one of them, the last one is locked in without getting into too much detail. All right, so how do you find these critical values? Well, just like with critical values of z, you can use technology or you can use a table. We're not going to be using the same table. For critical values of z, we use table A2. So there is a link in the description of this video that will take you to a website that has table A3. If you're using technology, you can use any number of degrees of freedom. However, this table A3 can only be used for select numbers of degrees of freedom. So you'll see in the table, without having it in front of me right this second, I believe it has every value maybe up to 30. And then after that, it skips a little bit. It starts off going by 5s, and then maybe it goes by 10s. So if you're using the table to find a critical value of t, but the table does not include the exact number of degrees of freedom, you could either use the closest value, or you can be conservative by using the next lower number of degrees of freedom, or you can do something called interpolating, which I have not been doing in these videos. That's a method just for estimating the critical t value. For example, if let's say my number of degrees of freedom is 42, and my table just has 40 and 50, I find the critical values that are attached to 40 and 50, and then I kind of estimate, well, proportionally, the number for 42 would be 20% of the way from 40 to 50. All right, it's not that difficult, but I think with so much technology available, it's really not necessary. Okay, a little bit about the shape of the student t distribution. It looks like a normal distribution. It is different for different sample sizes. The larger your samples are, the more it looks like a standard normal distribution. So here you see they've drawn the t distribution for the cases n equals 3 and 12. So in blue, you have n equals 3. In red, you have n equals 12. And then in green, you have the standard normal distribution. Okay. All right. So finally, wrapping up the key points, the student t distribution has the same general symmetric bell shape as the standard normal distribution, but it does have more variability. It has a mean of t equals 0, just like the standard normal distribution has a mean of z equals 0. All right, and the standard deviation of the student t distribution varies with the sample size, but it is greater than 1. And as I mentioned, as the sample size gets larger, the t-distribution gets closer to the standard normal distribution. All right, so we're getting to examples here pretty soon. First, the steps for constructing a confidence interval for mu. First, you want to verify that the two requirements are satisfied, that your sample is a simple random sample, and your original population is either normally distributed or the samples are large, at least 30. And assuming that sigma is unknown, which is usually the case, use n-1 degrees of freedom and find your critical t value either using technology or using the table. And then evaluate margin of error using the formula that we looked at a little while ago. E equals t sub alpha over 2 times s divided by the square root of n. Using that value for the calculated margin of error, take the sample mean x bar and do plus or minus e. So this is just, and we saw something similar in the last section. There are 3 different ways to write the confidence interval. Remember that what we're trying to estimate this time is mu, okay? So you can either write mu is between these two values, x bar minus e, x bar plus e, or I like to write it like this, x bar plus or minus e, or you can write it using interval notation. And then again, if you have an original set of data values, round the confidence interval limits to 1 more decimal place than is in the original set of data. But if you're using summary statistics, they tell correctly this time, round the confidence interval limits the same number of places for sample mean.